my PhD about 1 year after Professor Lộc at Kyoto University, and then I did my postdoc there. After that, I returned to Vietnam and start working in the Vietnamese German University since December. And in this university, my position is a lecturer and teaching mainly some courses related to water resources, like you see here, hydromechanics and distribution network, or modeling details of hydrosystems, flood management, and or flood machinery. My main responsibilities in the master program of water technology, reuse and management, and also in civil engineering of the bachelor program. You see, this Vietnamese German university is quite young and quite small compared to AIT, I think. However, we just built a new campus in Bình Dương province, which is very big as well. And you know, this university is established between Vietnam and the Germany governments, and in every program we have a partner university in Germany, and the degree we offer both from VGU and a partner university in Germany. And for example, in this master program of water technology, reuse and management, we are in cooperation with a partner university, TU Darmstadt in Germany, and about more than 50% of the lecturers are from German professors. Okay, before going into the main topic today, I would like to introduce you about this one related to reservoir sediment management. And actually this, because you know, I'm working in a laboratory in Kyoto University, where my professor is one of the leading experts in this field, reservoir sedimentation management. Therefore, I would like to take this opportunity to introduce to you. You see, this one is from the upstream, the catchment. And this one reservoir, when we built a dam here, the sediment actually will accumulate into this reservoir. And if we don't have any action, the sediment accumulation will cause problem to the lifespan of the reservoir and may reduce the functionality of the reservoir as well. There's some methods to reduce the sedimentation rate inside the reservoir. For example, from the upstream, we need to plant the forest to reduce the surface runoff or reduce sediment erosion from the slopes. Or we can use the check dam here, small dam, to trap the sediment or reframe sediment entering into the reservoir. And then we will use a truck to transport that stream. This one we call sediment augmentation or sediment replenishment. Or we can then build a sediment bypass tunnel to divert sediment downstream. Or inside the reservoir, we can do dredging or excavating to remove the accumulated sediment. Or we can, the flush of the sediment from upstream, we don't want the sediment go into or deposit into a reservoir. We can draw down the water level and then use the density current venting or flush the sediment downstream. Okay, now I would like to go into the main content of my presentation today. And in this slide, I would like to introduce you some problematic challenges in the Vietnamese Mekong Delta regarding the hydrology. You see, this one, the Mekong River Basin, and the Vietnamese Mekong Delta is the last portion of the basin. So we annually face a lot of problem. For example, flooding. You see, actually, I think you are very familiar with the Mekong River Basin in general, or the Mekong Delta in Vietnam in particular. but I would like to remind a little bit. Flooding in the Mekong Delta is very severe, especially in the past and in the upper part of the delta. Some areas inundation depth about 4 or 5 meters and lasting about 4 or half a year. Besides, we also face with drought or salinity intrusion. Actually, I have some joint publication with Professor Lộc regarding the drought or salinity intrusion in the Mekong Delta. And annually, the normal intrusion length is about 50 kilometers in general, or some estuaries, the intrusion length up to 90 kilometers, especially in drought 2015 or 2019. Riverbank and coastal erosion also not a severe problem in the delta. You see the maps, this one provided by our government monitoring the locations of riverbank erosion. And then you see many locations where riverbank has been eroded. And the coastal erosion also. One study found that about more than 50% of the coastline in the delta now is under erosion. And especially you see the cap of 𝐒𝐞𝐫 here. So far it was growing or accumulated with the sediment. However, in recent years, some research found that erosion took place in many places, and some places like erosion rates up to 50 meters per year. And we identify this problem with or associated with the 4 main drivers. The first one is sand mining or climate change. This one global issue, or sea level rise, also global issue, and it's really severe in Vietnamese Mekong Delta. And another driver is dam development in the upstream. And in this slide, I would like to introduce a bit about the drivers influencing mainly on salinity intrusion in the delta. You see this one, the riverbed, for example, this kind of schematic diagram only. So that within the delta, it is controlled by the upstream water flow from the Mekong main river. And if the transition water discharge reduced, it will increase salinity intrusion, and then vice versa. At the seaside, the tide or sea level rise also affect strongly salinity intrusion in delta. Within the delta, you see riverbed incision is one of the main cause of salinity intrusion, and we have one publication with Professor Lộc identifying or assessing the impact of bed incision on salinity intrusion or land subsidence also. Another one, the water use mainly for agriculture in the delta, not only Vietnamese Mekong Delta, but also the delta in Cambodia. They withdraw the water a lot for irrigation, and some diversion of water diverted to other basins, for example, in Thailand or in Laos as well, may also reduce the flow in the Mekong River. And here in this map, published by Professor Lộc in 2021, we identify salinity intrusion in different years, like from 1998 to 2020. You see the trend is increasing salinity intrusion so far, and one prediction by the government, they found that maybe this year is not the drought year, or salinity intrusion not only in the surface but also in the subsurface of groundwater. In this one, we have joint publication with Dr. Trần Đăng An. I think he also presented this one before. This slide, you see the locations of hydropower dams in the Mekong Basin. So far, by 2017, there are 64 dams has been completed with the total capacity of 80 cubic kilometers. And among this amount, about 50% of the volume or storage capacity contributed by only 6 mega dams in the Langkang Cascade. This one in the Chinese part. And you see for these 6 dams, actually now another dam has been completed. Now actually 7 dams in the mainstream in the Langkang Cascade, in fact. And within this dam, 𝐿 and 𝐶1 are the 2 biggest dams with the storage capacity about more than 20 cubic kilometer. And this show you the sediment trapping efficiency. You see the trapping efficiency calculated as the difference or the sediment trap in the reservoir compared to the inflowing sediment. And in this reservoir, 𝐿 and 𝐶1, as I mentioned, the 2 biggest dams having the trapping efficiency of 92%. Besides these already built dams, there are also plans to build a lot of hydropower dams, but smaller scale or diversion weirs in the basin of about 350 structures. In my research, I conducted, besides collecting the data from hydrological stations and conducting data analysis, we also conduct some field surveys. Actually, because I'm working in the JUSTICE project, which include mainly 2 parts. One study about geomorphology, and another PhD student will graduate soon, study mainly in salinity intrusion. And for my part only, I conducted 3 times of the field survey. The first time in 2017, we measure, you see here, the flow parameters or turbidity and salinity along these 4 estuaries or distributaries of the Mekong River. And the second part I measure in the transition 2018 to measure turbidity and the velocity, not only 2D but the vertical, almost like 3D velocity. And another time I measure in the compartments or in the floodplains of the delta in this part in 𝐿 district. We measure mainly salinity to turbidity and mainly turbidity distribution from the main river to inside the compartment. And this map show you the locations where we installed turbidity meter to measure since 2016. So you see this one in the Tiền River, one in the 𝐿 River, and one in the Pham Nao Channel. We use this turbidity infinity turbidity meter. And we measure with the intervals of about 15 minutes for the turbidity from 2016 to 2020. And after that, we increase to measure every 30 minutes because 15 minutes not really necessary. And we also installed 2 salinity meters in 𝐿 River. This as here from the low flow.
Hello, Dr. Ben, are you still there?
I'm sorry, can you hear me? Maybe my internet's not good.
Yeah, sure. I think you can start to share again. I think we were in slide number 8 when you explaining about. Yeah, I think so. About the measurement of turbidity. I think we started to lose a signal there. I think this one. Yeah, you could start with this one. Thank you. Maybe we can turn off the video for a moment. Yeah, we can turn off the video for a moment, but I think just to have a more stable. Thank you.
Yeah.
Yeah. Please go ahead.
So besides conducting the field surveys, we also install some monitoring stations. Like we install 3 stations to monitor the turbidity. One in the main river, 𝐶𝐸 River, and one in 𝐸 River, and another one in Pham Nao Diversion Channel. And we measure every 15 minutes from 2016 to 2020. And after that, we realized 15 minutes interval is not really necessary. Since then, we increased to measure every 30 minutes. And we also installed 2 salinity meters in the 𝐸 River. We measure also every 30 minutes. This data really unique, especially turbidity data. No, as my understanding, no one or no project do the same thing or measure with very fine temporal interval like in our project. From this slide, I would like to introduce the main findings from my research. The first one, the impact variations of the flow regime matrix. We use here 22 flow indicators from low flow indicators to the indicators in high flow as listed here. As you know, to study the dam impact on the flow regime or on the discharge in particular, we need to compare the flow downstream of the reservoir with that or those in the upstream of the reservoir. The difference will be attributed mainly to hydropower dams or reservoirs. However, because upstream of the Lankan Cascade dams, we don't have any monitoring station. Actually, there's some, but no one can access to the data. Therefore, we can say no data upstream of the Lankan Cascade. And because of that, I modified the methodology a little bit to compare the historical data at one station just downstream of the dams. And because, you know, dam for analyzing the flow at Janssen, the hydropower dams mainly completed. The first one in 1993, Manwan Dam completed in 1993. So we assume that before 1993, the flow is natural. And then we divide the time series into several periods. But the first period from before 1992 as the natural flow. And then we compare the flow after 1992 with the one before to understand how the dam impact. Actually, by that methodology, the flow alteration will be attributed mainly to 2 drivers. The first one is climate variability, and the second one is hydropower dam impact. And then we did literature review and analyze the rainfall to exclude or to understand the climate impact first, and then attribute to hydropower dam impact later. For this graph, I used this equation here, very simple. This one, the average flow every month or every indicator here, average flow from 1980 to 1992 as the natural flow. And then we compare the both dam with the pre-dam. This one, the absolute difference. And then we calculated the relative difference by multiplying 100% here. And by this equation, we classify the values based on this, like from -5 to 5% as no impact. From 15, within 15% will be slight or moderate, like something like this. Here, the results at Janssen station, station number 5. You see here just downstream of the Lankan Cascade. We see here in for the indicators in the low flow season, it decreased. Negative mean decreased. All indicators or all the flow in the low flow season mainly decreased from 1993 to 2008. And then increased in 2000 after 2009. Actually, this very stands because, you know, hydropower dams just reduce the flood flow and increase the transition flow, and this one is opposite. I will discuss later. For the indicators of the high flow, it may fluctuate, not very clear from 1993 to 2008, but very clear or very obvious after 2009, because, you know, many dams, especially the two biggest one, namely Nuôi Sa Đu and 𝐶𝐤1, just completed after 2009, so it reduced or increased. This one reduced the flood flow significantly. For other stations, like station number 9 at 𝐕𝐤𝐤 here in Cambodia, or at Tân Châu and Châu Đốc, you see the indicators in the low flow season increased significantly. However, for the indicators in the high flow season or flood season, it reduced after 2003 or more obvious after 2009, because many dams has been completed in the basin. I will summarize the discussion later. Here I just would like to show the results only, and this one just so you know, maybe easier to observe the results. This one flow duration curve, and you see at station number 5 here, no flow season as the black line, and low flow, low dam development from 1993 to 2008, 26 dams completed, and high dam development. You see in the low dam development, the flood flow is increasing, while the dry flow or transition flow are reducing. However, in the high dam development period, the flood flow reducing and the transition flow increasing. This one is very normal, but the green line is somehow abnormal or not normal. And you see, I show here the maximum discharge from 1980 to 2015 at station number 5 again. We see the black line for no dam development, and low dam here and high dam development here. You see the maximum discharge increased by 18% in the low dam development and reduced by 25% in high dam development. And for the minimum discharge, it's quite reducing over the time. However, after 2009, because of the contribution of mega dams in the Langkang Cascade mainly, the flow in transition increasing significantly. For all the station number 9, number 10, and 11, the pattern quite similar, but not very clear, because, you know, as moving downstream, the catchment, the contribution of the flow from the tributaries is quite significant, especially the 3S basin. So the signal quite not clear, but we can observe the trend quite similar with the station at number 5. And I would like to skip introducing or explaining. As I mentioned from the previous slides, I just analyzed the flow alteration from the observed data. And such alteration mainly attributed to climate variability and hydropower dams. First, I need to understand what's the impact of rainfall variability first. Therefore, I analyze the rainfall here. This map shows you the rainfall, the average rainfall from 1980 to 2019 or 92 as the pre-dam condition. And then I compare with the low dam development and high dam development for the rainfall. And we can see in this graph, for the annual, you see the rainfall is very stable. Some fluctuation, but they're very stable. The green line is the trend, almost no trend. For low flow development or low flow periods, the rainfall is a little bit decreasing, but not statistically significant. and in the high flow season as well. Some decreasing trends, but not statistical significant. And I summarize, or I compare the values of the rainfall in no dam development, low dam development, and high dam development. Actually, the numbers quite complicated, but I summarize here. You see, for low flow rainfall in the low dam development periods, the rainfall increases, but quite small, not significant. However, in the high dam development, the rainfall decreases significantly, a bit amount. In the high flow season, in low dam development, the rainfall decreases. However, in the high dam development, the rainfall increases significantly. And by comparing this rainfall pattern with the flow alteration in previous slides, I summarize in this slide quite interesting. Firstly, in the low dam development period, for high flow discharge, the discharge increased significantly, very big amount of increase. However, the precipitation or rainfall decreases. They are in opposites. And you know, usually in natural river or pristine river, the discharge is corresponding to the rainfall. If rainfall increasing, the discharge also increases as well. But this one, they are in opposite trends. And the explanation can be the shift of the timing of the tropical cyclones. This one they explain from one of very famous publication in Nature by Professor Dabi and his group. Another one maybe because of the dams with or having small capacity to regulate the flow. Or in general, they don't at all. This dam in the low dam development period didn't have enough capacity to regulate the flow efficiently. And in the low dam, in the low flow season, the discharge is decreasing, but the rainfall is increasing. Again, it is opposite, and this can be attributed to hydropower dam operations or irrigation or diversion, especially irrigation in Vietnam, irrigation in Cambodia for the Mekong, in the Mekong Delta, or diversion mainly like in Thailand or in Laos, mainly, or maybe in the upstream as well in China, but we don't have really good data in the Chinese part. And this one for the high dam development period as after 2009. In the high flow season, the discharge decreases, but the rainfall increases. This clearly because of the dams which reduce the flood process. And in the low flow season, the discharge increases significantly, while the rainfall also decreases significantly in opposite trend. So dams also increase the dry season flow. This one really understandable, and I think everyone can understand this one easily. I'm sorry, the findings, the analysis quite complicated, and the findings very complicated. I hope you can understand, or you may have some questions we can discuss later. In this slide, I will show you some evidence of reservoir trapping the sediment. The first one, I show you the station number 1. This one station upstream of like hydropower dams in the Langkang Cascade or in the Mekong River Basin in general. I collected the data from 1960 to 2003. You can see a clear trend, increasing trend, or the salmon increasing significantly. This quite very in a good agreement with the rainfall variability, because rainfall, or especially because of climate change, the rainfall is predicted to increase in intensity. And you know, the rainfall increase mean will increase the erodibility of the soil, or have more power to erode the sediment or increase the sediment yield in the basin. However, at all stations where I have the data at downstream of the Langkang Cascade, we see the sediment loss reduced significantly. Station number 2 here, Jensen, until the Vietnamese Mekong Delta, and the decrease is statistically significant. And really this from upstream and downstream, they are in opposite trend. Sediment supply from the catchment increasing, but sediment in the downstream areas are reducing. Therefore, this dam should be attributed as the main driver or the main cause of sediment reduction by sediment trapping. And in this slide, I show you another interesting results as station number 10 and 11 in the Vietnamese Mekong Delta. Firstly, for water flux, this one I plotted the monthly data of the water discharge here. The black line is the trend. We can see there's no trend, almost no trend. But the sediment in the same stations decreasing significantly. This really significant statistically since 1993 by using some trend analysis, some method like backdate test. And then I compare the sediment in the pre-dam period as before 1992 and the post-dam period as in between 2012 to 2015 at different stations like station number 5 and 11. You see in the map here, the sediment loss reduced significantly, especially like 90% at station number 5, or in the Vietnamese Mekong Delta, it is 74%. And within the Vietnamese Mekong Delta, I estimated that out of 74% of sediment reduction, 40% is caused by 6 Langkang Cascade dams. These dams contributed about 40% out of 74% of the sediment reduction in the delta. And among these 40%, 32% is due to Man Quan and Da Cho San dam alone. Man Quan, you see here, the first one built in the Langkang Cascade in 1993, and 𝐒𝐞𝐦 Da Cho San, this one. It means that for the flow, it's quite difficult to analyze the impact of dams. However, for the sediment, it's really clear or obvious by analysis. And the first dam which has been built will trap the sediment significantly. Although the reservoir capacity not very big, not necessarily the biggest one. And here I compare the sediment loss in the pre-dam period from 1960 to 1990 at station number 5, Jensen station here, with the sediment in the post-dam period in the Vietnamese Mekong Delta. Why I perform this comparison? Because, you know, as moving from upstream to downstream, the sediment loss will increase because of the contribution from tributaries. However, this one, the sediment loss in the delta, even in the post-dam period, is even smaller than the sediment loss at this upstream station in the pre-dam period. This shows you really the evidence of sediment reduction in the Mekong River or in Vietnamese Mekong Delta in particular. And we know that the sediment has a key role in stabilizing the geomorphology of a river system, especially in the delta. Is very important in maintaining the existence of the delta. Erosion or deposition of the delta is determined mainly by the amount of the sediment supply from the upstream river. And here, because that I found the sediment reduction significantly in the Mekong Delta, therefore I would like to understand what is the impact on the morphology in the delta. And I performed the analysis of the riverbed elevation comparing from 1998 to 2017, both from the field measurement, the first one I introduced you before, and from the simulation as well. In the upper part of the delta only, because I don't have the historical data in the lower part. This one show you the river forward along the Ting River, this river. The black line is the bed or the river forward in 1998, was very high. However, in 2017, the riverbed elevation is very low. Several meters of the riverbed has been eroded so far. And then I estimated the amount of riverbed incision. Here the red bars here, evolution volume. I estimated every 1 kilometer. You see, some areas have deposition, but mainly incision is dominant. And the volume, maybe volume quite difficult to imagine, but you see the mean evolution depth. You see some area more than 2 meters. That means the riverbed in some area, especially in the upper part near 𝐶𝐤, has been incised averagely about 2 meters or more. The same situation in the 𝐸 River, the lower river here. Riverbed incision is dominant, although there are some areas experiencing deposition, and the incision depth up to also some area up to 2 meters. Really significant. And here quite clearly for you to see for the cross section. I show some cross section like number 1, number 2, number 3, 4 here, comparing the data in 1998 to 2017. Some meters of riverbed has been eroded already, and 2014 is as the blue line. For all the cross section in the estuaries, we can see also by comparing 2017 and 1998, really significant incision already occurred. And I estimated that for the river forward, the mean incision rate during 1998 to 2014 about 33 centimeters per year. However, from 2014 to 2017, it is 1.24 meters per year, about more than 3 times. This I prepare the mean riverbed changes in 1998 to 2014 in this map, and this one the mean riverbed changes mean including incision and deposition. Here the changes from 2014 to 2017. I calculated the mean value because, you know, from this time series about 7 years or 17 years, and this only 3 years. So if we compare the absolute value, the total value may be not compatible. Therefore, I estimated the mean value every year. You see in this period, the incision depth, the mean incision depth about 16 centimeters per year, compared to this one about 50 centimeters per year, about 3 times more. I also established a numerical model using telemark 2D. In this one, you see the model I established using finite element method and triangle mesh. This one, some time series of the inputs, like the inputs at Tân Châu and Châu Đốc, and Cần Thơ and Mỹ Thuận here for the flow and sediment. And then I established 3 scenarios. One scenario, I used the data in 2017 as the input or the boundary condition. And then I used the same flow data in 2017, but I reduced the sediment loss by about 17.5% gradually from 2017 to 2026 as in the scenario 2. And then in scenario 3, I also keep the same flow condition of 2017, but I reduced the sediment loss abruptly or maybe abruptly from 2019 to 2020, based on the publication of Condorf 2014, or the final numbers is 75% of sediment reduction. And I found that in this figure, scenario 1 as the baseline, scenario 2, scenario 3, you see if the sediment is reducing, the riverbeds also experience more incision, especially the incision rate is more obvious or the highest in the Vàm-Nao diversion channel in this channel. And then the Tiền River experiences more erosion than the whole river. And you can see some values for the sediment loss here in the absolute values. In general, or in inclusion for this numerical model, in scenario 2, if we reduce 17.5% of sediment loss from the Mekong River, by 2026, the riverbed will increase the incision by 1.5 meters or increase 17% compared to scenario 1. And the number will be up to -2 meters incision in scenario 3 compared to the baseline scenario 1. And in the numerical model, I can simulate it, or I can find some scale developed inside the main rivers in Mekong Delta. And you see in this scenario 3, 80% of the sediment is reduced. I found about 22 scale developed. Especially we can see this scale was very severe, and these scale also very deep. I classify into shallow, medium, or deep based on the percentiles of the values. One important finding is that these scale are in the locations of the riverbank where it is eroded. You see, riverbank erosion is the same place, mainly in the same place with riverbed incision. That means riverbed incision has some influence on riverbank erosion, but we need to study more. And in the numerical model, I simulated the sediment dynamics in the delta. This one in the dry season, you see sediment concentration is very low. And comparing the sediment concentration in Tiền River and Hậu River, we see before the Vàm-Nao diversion channel, about 80% of the sediment is diverted or transported by the Tiền River, compared to only 20% in Hậu River. However, after the diversion channel, the percentage about 60% and 40% for the Tiền and Hậu River respectively. For in the flood season, you see the color, very high sediment concentration. And also the color in this part is very high compared to the sediment in this part, or in the values we see about 87% of sediment transported by this Tiền River compared to 30% in Hậu River. And in downstream of a diversion channel, the numbers are 65% and 35%. It's quite clear if we can see the effect of the Vàm-Nao diversion channel in diverting the sediment from Tiền to Hậu River. You see this one, the Tiền River red line. From upstream to downstream, the sediment concentration is reducing. However, in the Hậu River, sediment concentration is very low in this portion, and then suddenly increased downstream of this confluence because of the contribution from the Tình River. For riverbed incision, I attributed mainly two main drivers. The first one is sand mining, and the second one is sediment reduction due to them trapping the sediment upstream. Therefore, I collected this one mainly the secondary data from the published papers. The first data in 2015. The total sand mining volume in this year is 28 cubic meters per year. And another publication in 2018, including sand mining and dredging as well. The total volume is 29.3 cubic meters, million cubic meters per year. And these are the photo I took from my field survey and collected from the newspapers as well regarding sand mining activities in the delta. Now I show you some comparative numbers. Recap this figure I showed you before. In 2014 to 2017, the annual riverbed incision volume is 52.5 million cubic meters per year. And then I extracted the data here. This one for the entire Mekong Delta, 29.3 million cubic meters for sand mining. But for this area, for this bed incision, I estimated only in this portion in the Tình River, the upper part only. And because the data provided, the data of sand mining is provided in terms of by the province. So I need to take the total sand mining volume of these three provinces. This one, Đồng Tháp, I think Đồng Tháp, An Giang, and this one An Giang, two provinces here. The total volume of sand mining in this year for this upper part of the delta is 13.4 million cubic meters. And then compare this value with this value, I found that sand mining accounts for about 26% of bed incision in Vietnamese Mekong Delta, and the rest will be attributed to the effect of sediment reduction due to them trapping the sediment. And in this slide, because you know sand mining just occurs in local positions or local areas only, and I found that in this the upper part of the delta, in both two rivers, there are only 7 sites of sand mining. Therefore, I compare the contribution of sand mining to bed incision. I'm sorry. I'm sorry because I received some calls from others. So now I would like to restart. Here I compare at these 7 locations regarding the contribution of sand mining on bed incision. And I found that from the annual incision volume from 2014 to 2017 is 44 million cubic meters at these 7 locations. The areas is about 1 kilometer from, for example, in this, the location number 1, sand mining site number 1, I estimated incision, riverbed incision volume for 1 kilometers around this area, and another 1 kilometers and the total, the sum up of 44 million cubic meters. And the annual sand mining at these 7 locations is 16 million cubic meters. By dividing this to this number, sand mining contributes about 36% of local riverbed incision. This means that sand mining contributes quite significant to riverbed incision in the delta, but not the main, but not the most important on the top driver of the incision. All the driver sand mining, all the driver like sediment reduction is more important. To validate this kind of conclusion, so I show you here the one cross section around this area at the sand mining area. You see the irregular shape of the bed means or showing the sand mining activities here. And you see the extent of sand mining contributes about 30 or 40% of the cross-section area. It's quite relevant supportive for the finding of this value. I found another very important or interesting result. You know that in the dry season, because of the effect of hydropower dams, the river discharge should be increased. And we found the same results here at station at 𝐷 and 𝐶𝐷 station in the Vietnamese Mekong Delta. The dry season discharge increasing from 1980 to 2015. However, the water level at 𝐷 and Mỹ Thuận stations is reducing. I perform different water level indicators like the maximum water level or the minimum water level or the mean water level in the high flow season or the mean in the low flow season. All the indicators of the water level are decreasing. They are very opposite to the trend of the discharge. As you know, the river discharge increases will lead to the increases of the water depth. However, in this case, the water level decreases. It means that the bed elevation may be reducing, and it's really in a good agreement with the riverbed incision analysis I show you in this slide or previous slides before. And I also established the numerical model to estimate the effect of riverbed incision on water level reduction, and we found that it showed a good or promising results. If the sediment supply is reducing, for example 85%, the red line here, the riverbed will be incised accordingly. This one, the red line, compared to the measured data in 1998, and therefore the water level reduces accordingly again. And I found that the maximum water level reduction in Tình River about 68 centimeters, especially in the upper part of the delta, or in the Hậu River about 50% if we reduce 85% of the sediment supply from Mekong River to the delta. Here I summarize the important findings, which very complicated if I think difficult for you to observe the findings from previous slides, but this slide I summarized here. I found that the dry season discharge in the Mekong Delta is increasing so far. I mean, over the time. I did not discuss on the drought year, particularly the time series from 1990 to 2015, the dry season discharge increased, but the water level in dry season decreased. They are opposites here, and I found that it's because of riverbed degradation due to reduced sediment supply and apart from sand mining activities. And for the water level reduction, it may cause difficulty for water intake for irrigation, or may increase salinity intrusion. Of course, not only the reducing transition water level, but it is accompanied by in combination with the increased tidal amplitude or decreasing riverbed elevation. So we have some publication with Professor Lộc before regarding these findings. I think I would like to skip this one. This one kind of schematic diagram to explain the effect of bed incision on salinity intrusion increase. And finally, as we know that the flow regime in the Mekong River has been altered, and our objective to keep the flow relatively pristine. Therefore, we need to take some actions to reduce the adverse effects of flow alteration by keeping the mainstream flow for free, by like introducing some alternatives to dams, or may revise dam operation rule, or upstream countries should share the operation rule with the downstream country, or may they should supply enough water with good quality for downstream country to cope with, especially salinity intrusion. And for dam operation, or for the river management, we need to maintain the flow and sediment quite pristinely, or we should include sediment management techniques in the existing dams or the future planned dams. We should minimize transboundary or tributary impacts by introducing some collaboration between upstream and downstream countries. And finally, for the delta, we should revise some we should transform from hard structure to more adaptive non structural delta leading intrusion. Therefore, we should really re-evaluate the functions of look at construction in the delta or the dike system as well, because now there's almost no floods in the delta. So we need to revise, or we need to find the best solution to operate the dike system, the existing one. Yes, these are the publication or the references I used for this presentation, and I acknowledge it's a paper much. I would like to finish my presentation now.
You still there?
Yes, please continue, Professor Lau.
Yes, because I haven't heard from you for like 1 minute. So I think we are at your reference slides. So you might continue them. Yeah, thank you.
Yes, I finished my presentation, and if you have any questions, so I really keen on discussing with you.
Okay. Yes. Thank you, Dr. Pun. Actually, on behalf of all the attendees here, we feel very lucky and honored to be sitting here to listen to your presentations. I can see that a lot of data, a lot of findings that I believe that it takes you years, to come up with this one. So thank you very much, Dr. Pun, for being very open to share with us all of your findings, all of your hard work throughout the years. Before we move on to the Q&A session, may I request all the participants to turn on your video so that we can have a group photo session. Dr. Pun, may I request you to stop the share temporarily for the group photo session. Thank you.
Yes.
Good morning, Dr. Mohana.
Good morning, Dr. Locke. Good morning, everyone.
Welcome back. It's very good to see you again.
Good to see you.
Yeah, so everyone, please turn on your video, and I would like to introduce to for those of you who have not joined this event before, we have a very talented photographer here with us today, Mr. Roel, who have been very reliable in all of the photo taking. So Mr. Roel, please guide us on the photo session. Thank you.
Yeah, good morning to everyone. As Dr. Locke say, please turn on your camera for the photo session. So I will count 3. Everybody ready? Just wait for a while. Someone is still open the video, please.
Miss Sujata, are you is it convenient for you to turn on the video on Soul Sagasaki? Okay, there might be some technical issues. Yeah, I think you can just go ahead, Mr. Roa. Thank you.
Okay, so in count of 3, please smile. So 1, 2, 3. Okay, thank you very much for your presentation and welcome. Thank you.
Okay, thank you, Roel. So I would like to introduce to Dr. Ben here. Not only the students are joining, but we have Dr. Mohana Sundaram here, who is chair of our water engineering program. Very gladly joining here today with us. And we have a couple of PhD students, master students, thesis students as well. Some are actually working in very close area with you, Dr. Ben. Dr. Ben, can you turn on your video a bit? Okay, thank you. So I would like to open the floor for Q&A session. Maybe Kim, I think, because Kim is working on a, so I was talking about you, Kim. So you can also turn on your video and interact with Dr. Ben, because Kim is working for her thesis related to hydrological extremes of the Mekong Basin. So I think it would be a terrific opportunity. So Kim, please unmute yourself and ask the question directly. Thank you.
Hi, Dr. Bin. Thank you for your presentation. Can you hear me?
Okay. I think there is a problem with Kim's microphone. Is it okay if I can ask on your behalf, and then Dr. Ben can respond to you? Is it okay? Okay, so let me ask the question on Kim's behalf. So Dr. Ben, Kim understand that the data in Langkang on Chinese region of Mekong is quite difficult to get. So she's interested to ask whether you would use some satellite-based data estimate in your analysis, or if you did so, which satellite product did you use and would you recommend? Thank you.
Yes, thank you very much for your question, Kim. And actually, for my analysis, mainly I conduct on the observed data for the flow. However, I use the satellite data for the rainfall only, where I show you the maps before, and the data I used was sorry, I forget the name, RUC or RCU. The RCU data. It's kind of re-analysis data. We compare in that, you can find in the paper I published in Journal of Hydrology Regional Studies. I compare several kinds of satellite data for the rainfall, and then we came up with that CRU data.
Okay. Did that answer your question, Kim? You can. Hello, thank you, Dr. Ben. Does the information provided? Yes. Okay. Thank you, Kim. So, okay, thank you, Dr. Ben, for your question. Okay, I think we still have time for 1 to 2 more questions. So anyone, if you have questions, please ask directly to Dr. Ben. Thank you. Mr. Rabin, maybe you're working also on the hydrological alterations. You have any comments or questions to Dr. Rabin?
Thank you, Professor, for this opportunity. Actually, I'm working on the non-river basin in Thailand. So one of my objective is to find the water balance within the river basin. So I'm using the SWOT model to estimate the water balance in different sub-basins within that non-river basin. So it's interesting to know that different dimensions that you have discussed during your analysis to look into the impacts on the sediment on the dam. So I'm not looking into the dam aspect, but it will be interesting for me to further analyze the relationship of the different factors that contributes to the river discharge, the water yield. So it's interesting for me. I don't have particular question, but if I find any thing interesting and to further discuss with you, then I'll contact you. Thank you so much.
Yes, thank you very much.
Thank you, Rabin. Actually, Rabin is one of our doctoral students. I'm also in his committee. He's very good students. Okay, so Dr. Ben, I think time-wise is there. So on behalf of AIT team, I would like to say thank you for allocating your precious time and sharing your research with us. Since this is, since this is the first time, but I would like to share with you that we are running this web seminar on a monthly basis. It was before bi-monthly even. It means that we will have 2 seminars per year. So now you are already settled out in VGU. I'm really looking forward so that we can have some sharing session between the 2 universities, you can invite your students to come over or your faculty members to give a talk, just like we did with us, and also invited our faculty members or students to share, to elaborate the interactions, sharing of knowledge in the fields of hydrology, geology, and water-related disciplines. So that will be my request to Dr. Ben. Let's work together. And then also joint supervision can be something we can discuss along the line. If you can see that there are several meaningful associations between the 2 groups of research. So with that, I would like to again say thank you, Dr. Ben. Okay. Thank you again, Dr. Ben, and thank you everyone for joining this seminar. For the new students, just a reminder that there will be an orientation going on this afternoon, so please join. So with that, I would like to close this session. Thank you everyone, please stay safe, and we'll see you again. Thank you.
Yes, thank you very much.